In this problem, we investigate a property of abelian groups, which goes as follows. If G is abelian, G has order Mn with M and N relatively prime, and G has elements of order M and N, then G is cyclic. So therefore, G is isomorphic to Z mod MNZ. And if you look in Pinter, this problem has a little bit of a hint attached to it, which is to refer to a previous exercise. But I don't think we actually did that exercise. So I think what we'll do in this video is kind of tackle that while we're at it. So the proof then proceeds in a couple of parts. First is we let A be the element of order M and B the element of order N, respectively. And then we will study the element AB. And we will show that AB is a generator for G. Namely, AB has order NM. Now, we don't know what the order is, so I'm calling it K for the time being, but we're going to prove that that order actually is equal to NM. So here's how we're going to do that. First, we consider what is AB to the NM power. Well, that is A to the NM, B to the NM, since G is abelian. This is A to the M to the N, B to the N to the M, and M was the order of A, and N was the order of B, so this is E to the N times E to the M, or E times E, or E. And so, therefore, K, the order of AB, must divide NM, right? Because K is the smallest number for which you can raise to the power of and get E, and therefore any other power which you can raise this to has to be divided by K. So just turning it around, K divides NM. So that's one half of the proof. But now we're going to prove basically the opposite. So the other side is if I show that NM divides K, the only way that's possible is NM equals K, right? Because generally speaking, if the numbers are not equal, one of them is bigger than the other, and then they can't divide each other, right? The only way each divides the other is if they were secretly equal all along. So, towards this end, we start by taking the equation AB to the power K. That is equal to E by definition, right? K is the order of this thing. Since G is abelian, that's the same thing as A to the K, B to the K equals E, which in turn is the same thing as saying A to the K is equal to B to the minus K. So, whatever this thing is, let's call this thing X. Just for notational convenience. So, what is the order of this X? That's the question. So, since X is equal to A to the K, then the order of X, how do I say this? since we're looking at, cyclic groups, right? We know from cyclic group properties that the order of any multiple, here's a good way of saying this. Order of a multiple of A has to divide the order of A, which is M. So, in other words, the order of X divides M. On the other hand, exactly the same logic applied to B, right? The inverse has the same order as the original element itself. So, therefore, analogously, how do I say this? Where do I put this? Analogously, X also divides N. But M and N are relatively prime. That's an issue because the only numbers that can divide M and N are common factors, of which these guys don't have any besides 1. So therefore, X has to be equal to 1. But if X is equal to 1, right, we're saying X has order 1. Order 1 means identity. Well, let's remember where X came from. X was A to the K. So A to the K equals 1, and also B to the K equals 1. Or sorry, equals E. Right? These are the same thing. So now what we're seeing then is that, well, since M and N both divide K, and M and N are relatively prime, then their product divides K. This implies Mn divides K. And so now we've pretty much done it because we got K divides Mn, Mn divides K. So putting it all together, Mn is equal to K, AB equals Mn, and is therefore a generator. So I like this question quite a bit because, we're kind of just playing around with prime number, or not prime numbers, but relatively prime numbers and some basic number theory. I think it's a very illustrative problem of the kind of way that we think when we're doing group theory, right? Trying to leverage basic properties about orders of elements to squeeze out as much information as possible. But I don't want you to worry though. I do think this problem is probably a little harder than any of the ones we've done up until this point. If I were to give a problem like this for homework, and especially if it was somehow like on a test, I would give you guys significant amount of hints to kind of walk you through the reasoning. Like I would break this problem down a little bit to give you some idea of how to go about it. So no panicking, but still, nice problem.